Okay, your assignments that I've got graded are over there on the table. You can grab them on your way out. I'll take the homework, or I'll take the practice problems homework that was due Friday, but that I postponed till today. In the folder for today, there are some problems that are due Friday. So, and they're dealing with mostly the material in this lecture. Wednesday, I have scheduled a problem day to basically take some benzene rings and make different molecules out of them, and we'll talk about that a little bit today. So that's there's no quiz, there's no online quiz for Wednesday. We might have to have an in-class quiz. So, okay, any questions about these reactions? Let's see if I can get this. That's as big as it'll go. Even after you went through and listened to it, or not, Brian?
This might be a simple one, but why do we use Gilman reagents instead of Grignards?
Why do we use Gilman reagents instead of Grignards? Well, yes, except one won't. So, going back to like the Grignards, if we were to make a phenyl, what's called phenyl magnesium bromide. So I would take a benzene ring and I would react it first with Br2 and FeBr3 to put the bromine on, and then I would react it with magnesium metal to get the Grignard. So if I have this Grignard, the problem is I can only react it with carbonyls. If I tried to react this with, let's say, CH3CH2Br, thinking, hey, I've got a really strong nucleophile here, and I've got a primary halide, will it do SN2? The answer is it won't. Grignards don't do SN2 reactions. Now, the best coupling I could get out of this would be the phenyl magnesium bromide with the bromobenzene as I'm making the Grignard, and that's called Wirtz coupling, but that's a side reaction, not a real reaction. So I can't get Grignards to do this. If I could, that'd be great. And so what happens is that when we change the reagent over to having now a lithium and a copper in there, it completely changes the way the molecule reacts. And when if I add two of the, let's say, ethyl bromides to that molecule, then it would couple and I would get ethyl benzene. But the problem is that, so the mechanisms of these are, I don't know that they're well understood, but they involve a movement of a single electron. They're like a free radical reaction, except you never really get a true radical. So instead of moving the pair of electrons as a minus, as a pair, you move them like one electron, then a second electron. It's called a single electron transfer reaction. And so the mechanism changes. And again, how exactly that occurs, I'm not sure. I'm not up on my Gilman. The structures of these, though, are, the structure of this would probably actually look something like this, where you would have a benzene ring, and then you would have you would kind of have like the benzene rings, and the lithium copper in like a diamond. And you'd have to know what that is before you could even figure out the mechanism. So I mean, I did my graduate work on looking at these kinds of structures minus the copper, because copper's a pain. And so it would look something like that. Somebody told me at some point I should do like lithium cuprates, and I said no. I'll just stick with lithium compounds. And the stuff we've done, and I've done since with copper's the biggest pain in the butt element there is, because the compounds come out in 5 different shades of colors. They never do what you want them to do, and so they're really hard to control. So when you find a reaction where you can control it, you use it, and it's really difficult to find out how it works. But there's going to be an element of free radical mechanism here that's enhanced by this one, but not by the Grignard. So that's why we have to use the Gilman. But the problem with the Gilman is that it's air sensitive. So we can't use water. We have to really protect those reagents, or they will react with water just like a Grignard and they die. You pull off a proton and they're gone. So that's where the rest of the reagents kind of come from. These are all like metal reactions, but they're not air sensitive. They're not water sensitive. And these kinds of reactions are actually some of the ones that they would actually do in a pharmaceutical company nowadays. They wouldn't use a Grignard, they would use some of these Suzuki and Heck couplings. So this is as close to the modern organic chemistry as we're going to get in terms of what happens when a pharmaceutical chemist decides to sit down and synthesize a drug. They're going to use reactions that look like this, not the reactions we learned the rest of the year. But you got to learn this year's reactions before you begin to look at the other ones. That's my long answer with some commentary. What else?
Could you actually go through the Suzuki coupling, see what the problem is not?
What kind of coupling?
Let's do the boronic acid.
How do you make the boronic acid, the Suzuki coupling? Well, I can't give you the mechanism of that because that's beyond the scope of the course.
Okay, well, no worries.
So, but the whole idea here is that to do the Suzuki coupling, what we need to do is we need to first of all make the boronic acid. And so that's where the issue comes from. So let me go back here. So the easiest way to make the boronic acid is to think about this as something that we've already done. And I need to get rid of the circle because I need a cyclohexane. So if I had this alkene and I'm going to react it with H, B, and then 2 ORs. Okay? We've done this reaction before, just not with the 2 ORs. It was last semester, and what we did was we reacted this so that the double bond reacted with the H and the boron in something that looks like this, to form then a square transition state. So in the boronic acid part, the BH bond is going to break to form the boron carbon bond. Then the double bond is going to break to form the CH, the top CH bond. So that what I end up with is the C attached to the H, and then down here, the C attached to the boron. So that's the first step in BH3, H2O2, hydroboration oxidation. So with all this stuff, I didn't have a lot to build on from reactions that we had previously done, but this was stuff that we had done before. So my question would be, where does the boron add? So if I'm going to do that with this cyclohexane on top, where am I going to add the H? Where am I going to add the boron? It's anti-Markovnikov.
So H adds to the bottom of the carbon and then the ORS.
Okay, so if I label those A and B, where do you want to add the H?
Oh, sorry. A.
Final answer. Do we agree it's going to add to A? Well, if BH3 H2O2 is anti-Markovnikov, the hydrogen adds to the carbon with the most substituents. Normally, under Markovnikov's rule, the hydrogen would add to the carbon with the least substituents of the carbon with the most hydrogens. So in this case, the hydrogen's got to go to A. So the hydrogen will add to A, and the boron, in this case with the two OR groups, will add to carbon B. So sterically, the boron adds to the least sterically hindered carbon. Now, what am I missing here? No, I'm good. No charges. Stereochemistry. So how did the H and the B add? Cis. So they added cis. And you might say, why did they add cis? Because down here, the square is only big enough for the H and the boron to add to one side of the double bond. It's not big enough for the H to add and then the boron to like swing around. Not going to happen. So this is how I can make any boronic acid that I'd like. And now what I want to do is now I want to take that boronic acid and I want to couple a group to the boron. So once I've got this, I want to replace that with some group. And since we're talking here about the Suzuki coupling, what I'm now going to do is I'm now going to take my boronic acid that I just made, and I'm going to couple it with bromobenzene. Or actually I can couple it with probably any alkyl halide. And so when I do that, that's when I use the palladium on carbon with the potassium carbonate. And those are the reagents that they used. There's a lot of transition metals and expensive metals like platinum and palladium that are used for these coupling reactions. I would care to venture that their mechanisms are not necessarily that well known. Other than I would suspect that the boron and the halogen somehow attach themselves to the palladium, and at the surface, that's where the reaction occurs. But exactly how, I don't think we have to concern ourselves with that. This is an example of an organometallic reaction. So you've got your organic part, you've got your metal part. The palladium on carbon, palladium's super expensive. So if I, instead of taking a chunk of palladium where all the inside of the palladium except the surface is going to be useless, if I could coat the palladium onto carbon, it's going to be far more cost effective. And so then I've got my thin layer of palladium on the surface, and it causes it to react. So what did I end up doing? I ended up coupling this, which I can't write on, that benzene ring, this part, I ended up coupling to then this entire part. So wherever the boron was, that's where it's going to be attached to the benzene ring. So the carbon with the boron, the carbon with the bromine couple together. So with this one, I need to prepare the boronic acid. And so that's where we can look at what we did last semester, which is react the alkene with the dialkyl borane, or we could even react a triple bond with the dialkyl borane and end up with a double bond down here. So that was relevant from last semester. So each one of these reactions, whether it's Heck coupling or in this case Suzuki coupling, they all have a key feature where you're basically going to take two pieces of the puzzle and bring them together with a transition metal catalyst. What else? Go.
Doing these tests and stuff, do you want us to put the name of the reaction on, or do you?
If I ask for it.
Okay, so it's just good to know everything. The name of the.
These names, I'm going to be honest, I probably would get confused between the Heck and the Suzuki. Gilman, no, Gilman's unique enough, but the other ones are just like, okay, is it palladium? What has been coupled? So I wouldn't ask you for the names of the reactions. And to be honest with you, I might more likely ask you to write the products of the reactions than I would say, here's the reagents. But
Those are like a little bit more.
yeah, they're a little bit more complicated because now we're like venturing into like the real world. Like all the other stuff we haven't learned is real world, but this is now the kinds of reactions that people do on a daily basis. But the importance here is that if you're really making real live organic molecules, like something that's new or something that has a potential use in a drug as a drug, it's going to be really complicated. And you might have a certain benzene ring with 3 different functional groups on it. And you may be trying to take that benzene ring and now add a 20 carbon piece to it. Right? Because that's the only way you're going to be able to make that potential drug molecule. And so a lot of times what happens is in those molecules, they decide to cut them in half or thirds and say, you know what, you go make the benzene ring part of the molecule. I'll make the alkene that I'm going to turn into the boronic acid part. And then we're going to take our 2 parts and we're going to have to figure out a way to couple them together. And so you might have 2 or 3 groups of people working on each part. And then at the end, they need a way to couple everything together. And so carbon-carbon bonds are huge. Like prior to 1950, if you had a reaction that formed a carbon-carbon bond, you're automatically in an organic textbook as a named reaction. And most likely you won like a Nobel Prize. Nowadays, that's the prime target. Find a transition metal and 2 pieces that I can put together in my drug molecule. Although now there's more reactions, so there's a little bit less of an important. But I do think Suzuki, if he hasn't won a Nobel Prize, that group they will, because that's a well-known reaction. Heck, I'm not sure. Gilman never did. He never won a Nobel Prize because it was similar to the Grignard. But that's the key, is forming the carbon-carbon bonds. So that's where these reactions become important. And where they might become important to you is, we'll get to that before the end of the class, because if I gave you some benzene ring with some complicated alkane, and you remembered these reactions, then you could just take that complicated alkane and the benzene ring and stick them together. Whereas you normally would have to put the carbon chain on there and then start playing with all the functional groups. Sarah, you had a question?
I was just confused on the Suzuki couple. Like, so for specifically the example the H and then you added it antimicrobial, like how would...
Actually...
Isn't that like now time? So when you did not...
So where it says cis anti-Markovnikov here, I'm reminding you of how the H and the BR and the BH2 added. That reaction isn't Markovnikov or anti-Markovnikov, if that's causing the confusion. So this reaction isn't. I'm just saying when you add the H and the BH3, it has to add cis anti-Markovnikov. But in this case, that's not that reaction. And the same thing would be true for the alkyne. In this case, I did add anti-Markovnikov because I added the H here and the boron over here, and I added the H to the carbon that was most substituted. So this one was cis and anti-Markovnikov. What we did last time was we took this molecule, added peroxide to it, and turned the boron into an OH. So that's what I'm reminding you of, is we've seen this reaction before, just not with the 2 OR groups. I'm reaching for as much previous stuff to relate this to as possible. And that's all I got, outside of Gilman. The other part of this was nucleophilic aromatic substitution. So in the nucleophilic aromatic substitution, I've changed the rules. So what I'm now doing is I'm now substituting the methyl group, or in this case, I'm going to substitute the chlorine. So nucleophilic aromatic substitution, you substitute what we would normally have as a traditional leaving group. Chlorine, bromine, OH. And I'm going to substitute them with a limited number of nucleophiles. So before it was electrophile, now it's nucleophile. All the rules are changed. 2 nitro groups and electrophilic aromatic substitution would make the ring more or less reactive. If I put 2 nitro groups and try and do electrophilic aromatic substitution, what do the nitro groups do to the ring? They deactivate the ring. But since I've changed the rules 180 degrees, they activate for nucleophilic substitution. And so in this case, what can happen is, if I wanted to take, for instance, this chloro-nitro group, and I wanted to add hydroxide to it and substitute the chlorine for an OH, which would be a pretty nice reaction to do, right? Because if I want to substitute a chlorine with an OH, I can't do that right now, other than this. To put an OH on the ring, how many steps does it take me? To put an OH on a benzene ring, how many steps does it take? Well, let's see, I got to put an NO2 on the ring, right? Then I got to reduce it to an NH2. Then I got to turn it into a diazonium. And then I got to add H3O plus to it. That looks like 4. Whereas if I just had a chlorine on it and I could somehow replace the chlorine with the OH, that would be uno step. But that works best when the ring has lots of nitro groups on it, because that activates the ring for substitution. So that's where the OH comes in, adds to this carbon. That pair of electrons moves here, and now I've got a negative and a positive charge. I've got the negative charge next to the positive charge, which means that basically I can write a whole bunch of resonance structures. So in this, well, let's go back. When I was talking about groups being ortho-para or meta-directors, it was either good or bad to have the positive charge next to a substituent. Because if that group stabilized the positive charge, what kind of director was it? Should probably repeat the question, right? Because you weren't prepared for it. When I was talking about the mechanisms, this was before spring break, so it was like a month and a half ago. Whenever the plus charge ended up next to the group, and that group stabilized the plus charge, how did it direct? Ortho-para or meta? Ortho-para if it stabilized it. What if that group destabilized it? Then it was meta. So there's an overarching principle. Same thing happens here. If I'm going to do substitution, my negative charge, my nucleophile is going to come in and add to the carbon it's going to substitute for. That's going to put a negative charge next to it. Whatever group I can put next to that negative charge to stabilize it makes nucleophilic substitution more likely. And so, in this case, putting nitro groups stabilizes it. 1 nitro group, not bad. 2 nitro groups, even better. because there's more resonance structures I can draw. So typically we only really talk about doing nucleophilic substitution that goes very quickly if it's got a couple of nitro groups on it. And it'd be best if they were ortho and para to this, to that, and then so then you get all those resonance structures. Now there was, you might say, whatever. Does it really matter? And the answer may be yes, depending on the kind of molecules you want to look at. Now it's unusual for molecules to basically have like lots of nitro groups on them, except one very famous molecule, which is trinitro toluene. Right? So there's like billions of tons of trinitrotoluene in soils all across the country, because there's been lots, not necessarily lots of bombs dropped on the U.S., but there's been a lot of development of and production of TNT. So there's lots of environmental issues in cleaning up soil and getting rid of the TNT. And one thought was, well, is there a way I could substitute the methyl group with like something else that maybe the microorganisms in the soil will eat easier than TNT? Because I don't think there's any microorganisms that really have a taste for TNT. They haven't found them. And we'd be probably better off not to invent new microorganisms, right? Because in all the movies and documentaries I've seen, that ends bad, right? When we start, mutating stuff, that's a bad thing, right? So you would think maybe some sort of nucleophilic substitution would work, because the nitro groups are in perfect positions to stabilize any kind of anion that's produced. And so there are a lot of people working in the Army and in lots of different research facilities trying to figure out, okay, can I convert TNT into something that's biodegradable? Because right now it's not. And then you get the TNT in the drinking water, and it's a huge environmental problem. So are there ways to do that? And this is one example where I think somebody proposed this as a seminar, and I think we argued for about a half hour whether you could do any of these reactions or not. But that was one thought. So those nitro groups are actually kind of important in these molecules. That would be just one example. If it's not an activated group, then we got a big problem. Because if it's not an activated group like this one, where you've got a chlorine with a methyl group, then you have to go to super high temperatures to do that substitution. And when you do that substitution, what you end up with is two different products. So if you tried to take the parachlorotoluene and reacted it with NH2-, you would end up with two different products. Now, when people did this, they couldn't really reconcile the mechanism getting two products. And so that's where they had to come up with the Benzine Intermediate, the famous Benzine Intermediate, where you've got a benzene ring now with a triple bond inside of it, that has all sorts of problems, right? A triple bond's supposed to be linear. How do you fit that in a 6-membered ring? Well, if you do, it's going to be really super unstable. So, but that was the only mechanism they could really reconcile with this. So the nucleophile, the NH2, could add to one carbon, or it could add to the other carbon, and that's why you end up with 2 products. That's consistent with that mechanism. But that's not the best way to do substitution on an unactivated ring. So a lot of times what you'll see is the activated with the nitro groups. And those are the best groups to use. So those mechanisms, I'm going to ask you to do at some point. You can go back, look on old tests. We've done those mechanisms. Now, what we want to do is we want to be able to make substituted benzene rings. And I want you to be able to use all the reactions you know in converting the benzene ring into, I don't know, maybe I've got a CH2, CH2, CH3 group here. That's pretty boring. And then maybe down here I've got a CH3 group. So how do we approach these reactions if I just give them to you? And what I should probably do is go back to the blocking strategy that I forgot about the other day. I didn't really forget about it. But there are ways to make these reactions occur a little bit better. So the key reaction with thinking about blocking and unblocking was this. I could put an SO3H group on the ring with H2SO4 and SO3. But I can take an SO3H group off the ring with steam. And blocking means what it sounds like. I want to block the position with an SO3H group, and when I'm done blocking, I want to remove it. So here's a classical example, or my classical example, which probably isn't that classical. I want to take my benzene ring, and I want to put a methyl group here, and I want to put a bromine here. And I'm working for a company, and somebody said, hey, I want you to make that. And so I'm sitting down trying to say, well, let's see, can I make it and make a profit? Right? Because otherwise, then I can't make something and lose money on it, unless I'm working for the government or other various industries that lose a lot of money. I'm only going to be able to do that a couple of times before I'm out a job. But I want to make this in its highest yield possible. So you might say, what would you do? Actually, you know what? That's not the one I want. That's the less classical. This is the one I want. I want that one in the highest yield. So what group do you want to put on first? You want to put the bromine on first? Okay. What? BR2, FeBr3. Okay? So then I put the bromine on. Now I want to put the methyl group on. So what am I going to do there? CH3Cl, AlCl3, and so what am I going to get? I'm going to have the methyl group at ortho and para. Which one of those two do you think is going to be the major product? Probably para. Right? Because of steric hindrance. We haven't taken steric hindrance into account yet, but now I've suddenly put myself in charge of this imaginary company where I'm going to take everything into account. Because even if I got this reaction to go 50-50, I'll be able to sell this, but then what am I going to do with the rest of that? Well, that's a good question, right? Maybe there's another buyer that'll buy it. And what if there's not? You know, I don't think I have a waste jar big enough to put in, let's say, the 2 tons of byproduct that I'm going to get. So one of the things I can think about is, well, let's block. How about I block the para position and force the methyl group to go ortho? So what would I do with this molecule? I'll add SO3H and H2SO4 to it. And where will the SO3H group go? It'll go para to the bromine, and now I'm using sterics to my advantage because the SO3H group is going to be pretty big, and so very little of it is going to go next to the bromine. So I'm going to get almost 100% para. So now when I force my methyl group, now when I say, let's go ahead and add CH3, Cl, AlCl3, where is that going to force the methyl group to go? To ortho to the Br. Because the Br is still the director. Because it's higher up than SO3H. So now I can force the methyl group into the ortho position and then do what? And now do what? Now I can react this with steam and strip off the SO3H group, leaving my desired product behind. So now I'm not throwing away a lot of product, or I'm not having a lot of byproduct that I'm either going to have to dispose of or figure out somebody else to sell it to. So that is what's called a blocking strategy. You can block the para position by putting a group there, but you can only block if you can unblock.
So you not like the
No, we use SO3. We actually probably sulfonate benzene rings a lot. But in this case, it's being used in sort of an atypical way of blocking. Now, my only question, if I was really doing this, because I'd have to sit down and I'd have to think this out I'd have to think it out a little bit to make sure that, that I am going to be able to make some sort of profit on this. And for those of you that don't care about profit, anything that I make as waste goes into the environment. So my experience is people that don't like profit, like the earth, that's not a mutually exclusive position. You can't like profit and earth, but that's a class for another part of the university, and I increase like chances of getting hit with a bias charge if I go any farther. So if we're thinking purely environmentally, I would like to do this reaction in almost 100% yield every time. I would like to use every atom and not use any as waste. Right? This is called green chemistry. It's actually a field. But if I'm sitting down and looking at this even from the energy standpoint, would I want to put the bromine on first, or is there an advantage of putting the methyl group on first? And in that case, I'd have to look and say, I'm trying to methylate a very deactivated ring down here because it's got 2 deactivating groups. I probably would be better off to put the methyl group on first, because then I've got an activated ring that's going to take less energy to react. And so if I did that, I would just do the same series of steps. But it's really, you have to take into account all of those things, not so much when we do things in the lab, right? Because we're doing small scale, and we don't care how much energy we put from the hot plate into the reaction, because we just turn it up all the way, right? As long as we're not burning ourselves or melting anything, we're fine. But when we go to making, 2 tanker car quantities of this stuff, we got to be a little more careful with our energy consumption, because we're going to scale this up a lot. So that's where I might take into account and think, okay, well, which one of those would be the best way to approach things, both from the yield standpoint as well as from energy, as well as what's called atom economy, which is making sure that you have as few waste atoms as possible. But this would be one example. So these are the kinds of problems that we want to be able to do. So the problem I gave you before, that propyl and methyl, what series of reactions would you do to get that product? And not only what series of reactions, but you got to get them in the right order. And it's going to take thinking about all of our reactions. Because if I'm going to just put a plain, ordinary alkyl group on the ring, that's easy. What if I want an OH here? Oh no, that means we have to remember previous reactions. Benny?
So you mentioned it today on in-class quiz, so possibly.
Yeah, I did possibly mention that, didn't I? I would have possibly forgot it.
Okay. Well, you last time you gave us like something to study, so I was just wondering if you.
How about all of the notes from today?
Okay.
How about the different reactions for Wednesday? So in other words, here's the quiz on Wednesday. I will give you reagents, and you have to write the products. The coupling reactions, and you have to write the products. So I'll give you a Suzuki. I'll give you a Gilman. I'll give you a Heck. I'll give you nucleophilic substitution. Okay. But I won't ask you the reagents. Instead, I'll ask you the products. Okay. So that's what the quiz will be, and that's what the quiz was going to be anyway. All right. So that'll be our in-class quiz, and then we'll start. I'll give you some problems like that, and you can work on them and see how far you get. And that's what we'll be doing on Wednesday. Homework can go on the table in a pile, and then you can take your problems.